All right, so looking at number 7 first. We have a monkey on a sled. Sled, and there's a monkey. Okay. He's moving at 4 meters per second. Okay. Does he have kinetic energy?
Yes.
Yeah, right, because he has mass and he has velocity. Now, with his kinetic energy, he is going to start going up an incline that is 25 degrees to horizontal. And when he hits that incline, so let's say he's up here on the incline now. I don't know what happened there. He is going to slowly come to a stop, right? Why?
Gravity.
Friction is acting on him and gravity is acting on him, right? So there's going to be actually two forces pulling him down the incline. One will be what we call FGX, right, which is the force of gravity down the incline. We learned how to get that value in chapter 5. And the kinetic friction force also will be directed that way. Both of these forces will be doing positive or negative work. Negative. And they will be taking away the kinetic energy that he started up the hill with. So, to figure out how far he goes, using the idea of work, there's your displacement there, we need to figure out what these forces are. So first, the FGX let's get. And let me put down that the monkey and the sled have a mass of 20 kilograms, and that the coefficient of kinetic friction is 0.20. So FGX, you remember that when we did problems on an incline, that we would have the weight down, and then you had to find your components, right? And this we called FGX. This angle is theta, which was here, and FGY. So FGX was FG sine theta, right? And FGY was FG cosine theta. So that's how we're going to get FGX. So FGX is going to be FG of the monkey and sled, which would be 20 times 9.80. So that's the weight of the monkey, and now you take the sine of 25, and you find that the force down the plane is 82.8 newtons of gravity. So FGX is 82.8. Friction, FG, or FK, is mu K Fn. So mu K is 0.20. Fn is going to be mg cosine theta. So 20 times 9.80 cosine 25. And so we find the friction force is 35.7 newtons. So this is 35.7 newtons. Okay. Now both of these forces are doing negative work, right? And the total work that they do is what changes the monkey's kinetic energy. So now let's go to the work energy theorem and figure out how far he goes. So what we know is that the net work equals the change in kinetic energy. And the net work is going to be done by these two forces. So let's put in an equation for work that incorporates d and the value of the forces. So FD cosine theta, and since we're combining forces here, this is actually, F is going to be the two forces. So we're looking at the work done by the net force equals 1/2 mvf squared minus 1/2 mvi squared. So the total force is going to be these two, 82.8 plus 35.7. How far up the incline he goes is what we're looking for. And the cosine, what's the angle between the direction of the displacement and the direction of the forces? No, common mistake, right? The displacement is up. Josh, you had it right. The displacement is up and the forces are down, right? That is 180 degrees. So it's not the angle of the incline, right? It's the angle between the displacement and the force, right? If displacement's that way and force is like that, that's 180 degrees, okay? So 180. And that's because these forces are going to do negative work. They're going to take away the kinetic energy. Equals, now, what is the 1/2 mvf squared of the monkey? What is his final kinetic energy going to be, in other words? Zero. Minus his initial kinetic energy, which was 1/2 total mass times the initial velocity squared. And now you just solve for d. And so d is 1.35 meters. In 9, we have a truck that is 1.50 meters off the ground. And we're going to look at two scenarios of moving a refrigerator onto the truck. In the first scenario, which we'll do right here, here's the refrigerator. The movers want to lift the refrigerator up and move it on the truck. Okay. The weight of the refrigerator is 1,200 newtons. So Fg for the refrigerator is 1,200 newtons. And they're going to need to lift it through 1.5 meters. So the work they're going to do in doing that is going to be, they need to apply this much force to the refrigerator. So 1,200 through a height of 1.5. What is the angle going to be between the force and the displacement? 0, right? They're lifting it up. So the displacement's up, force is up. So cosine 0. So to put it on the truck is going to take 1,800 joules of work. The other option is to attach a ramp to the truck and put the refrigerator on a ramp. Right? There. Now to get it up there, instead of lifting it, they're going to slide it up by applying a force pushing it up the incline. So what we want to do is find what is the force that they're going to push with. And that force is what's going to do the work. Now, back to the incline again. We need to know how much force is going down. And whatever Fgx is, right, that's going to be how much they have to apply up. So from the same reasoning we did in the last problem, Fgx will be Fg sine theta. So now you got 1,200 times the sine of an angle. Well, the dimensions of the ramp are such that this is 1.5, and the problem tells us this is 5. So that means that our ramp is making an angle of 17.5 degrees with the horizontal ground. So this is then 17.5, making Fgx 360 newtons. So now we know that gravity is pulling down the incline with 360 newtons of force. That means we need to push up with 360 newtons of force. Is everybody on board? Rachel?
Is there friction?
No, not yet in this problem, but I'm going to talk about that in a second. Now, let's figure out the work they do to move it 5 meters, right, with 360 newtons of force. So Fd cosine theta. Now, instead of using 1,200 newtons to lift it, they're only using 360 newtons. But they're applying that 360 through the length of the ramp, right? Through 5 meters. And what is the angle between the displacement and the force? Somebody. 0, right? The displacement, again, is up, and the force is up. So therefore, that's a cosine of 0. And you get 1,800 joules. So in which case, this one or this one, did it require more work to lift the refrigerator onto the truck? Same. Which case is it easier? The ramp, right? Why? Because less force is needed. Right? If you use less force, your work should be a little easier. It's a more distance, but big deal, right? It's much easier to go further than it is apply more force. So this ramp is a type of what? Does anybody know?
Simple machine.
Simple machine, right? What kind? Inclined plane. And we're going to look at those at the end of the chapter. Yeah. So simple machines make the work easier. They don't make less work. They make them easier. Now, Rachel brought up a good question. What was your question, Rachel? Why is there no friction, right? That's because we wanted to show that the work is the same, but that's really not true, is it? Because if there were friction, which way would it go, Rachel? Down, right? And that means that, let's say the friction was 40. So if the friction down were 40, that changes this force, doesn't it, to what? 400, which changes this to 400, which changes this to 2,000. So if you really use a ramp, you're actually going to do more work because you got some friction than if you don't. But again, I'd rather do 400 newtons of force than 1,200 newtons of force. So even though you're doing a little bit more work, some of that work is being taken away by friction. It's still easier. Is a refrigerator on a horizontal surface, and we are going to be pulling it with a force this way of 240 newtons, and that force makes an angle of 20 degrees with horizontal. The mass of the refrigerator is 85 kilograms. Coefficient of kinetic friction is 0.20. And we're going to move the refrigerator through a distance of 8 meters. And that's all the information we have. So first, part A is find the work done by the force, 240. So work is FD cosine theta. So that's going to be 240 times 8 times cosine of what's the angle between the force and the displacement? 20 degrees. So that is 1,800 joules. All right, so the work done by the force is 1,800 joules. Now we need to know the work done by friction. Again, FD cosine theta, but now this F is going to be friction. So let's find the friction force. To find friction, we need to use UKFN. Now, mu k is 0.200. Let's quickly look at the free body diagram for the refrigerator. Fg is equal to 85 times 9.8, which is 833 newtons. Now, how many forces are going up on this free body diagram? Two, right? One of them is the y component. Here, Fy. To get that, you would do 240 sine 20, which is 83, I believe. Yeah, 82 newtons. So if you have 82 newtons of y component here, that means your normal force is not equal to 833. It's equal to 833 minus this, which is 751. Does everybody follow that? Okay. So now you do 0.200 times 0.751 and get 150 newtons as your friction force. What's that? Not point, sorry, 751. Good catch. So now we know that there's also a friction force here of 150. Now let's calculate the work that that force does. So that's going to be 150. Also applied through 8 meters. Cosine, what is the angle between the friction and the displacement? 180, right? Friction will always do negative work. It'll always be 180. And there you got negative 1200 joules. So the friction does negative 1200 joules of work. Now let me ask a question about this. What was the initial kinetic energy of the refrigerator? Started from rest. 0. Will it have kinetic energy at the 8 meter mark? That's 3 answers, right? Will it have it? Garrett's saying yeah. Why do you say, oh, you're just,
I don't know why.
oh,
I'm just throwing it out there.
okay. That's good. How do you give something kinetic energy? No. I mean, it has kinetic energy velocity, right?
Work.
What?
Work.
What kind of work?
Positive.
Positive, right. To give it kinetic energy, you do positive work. So did we do positive work on the refrigerator? Yeah. Did we do negative work on the refrigerator? Yeah, in the problem. Was there negative work done on the refrigerator?
Yes.
It was while we were doing positive work, right? Of which was there more, positive or negative?
Positive.
So doesn't that mean then that there was more positive work done? So that means there, overall there would be positive work, meaning, and positive work becomes what? Kinetic energy. So does it have kinetic energy?
Yes.
Yeah. How much? Yes, you do know. 600 joules, right? If you did 1800 and 1200 of that was taken away by friction, that means you left with 600. So now it has 600 joules of energy, kinetic energy. What?
That means it's going to keep moving.
It's going to keep moving, right? Until
So you push it for 8 meters, but then you stop pushing, it's going to keep moving a little bit
it's going to keep moving until all that 600 is gone
by the friction.
by the friction. Very good. Where does that the energy that friction does go? Go like this. That's friction, right? Heat, right? Don't your hands get warmer? Friction becomes heat. Okay? So that's what's going to happen. The floor, the refrigerator, they're going to get a little bit warmer as that energy becomes thermal energy. Refrigerator problem, the first question is asking, if the refrigerator started from rest, how much kinetic energy does it have after it hit a slid 8 meters? Okay, so we know that in going 8 meters, we did 1800 joules of positive work. And while we were doing that positive work, friction did negative 1200 joules, or 1200 joules of negative work. So the net work for, or done on the refrigerator is, so the net work is 1800 joules plus negative 1200 joules. Right, for a total of 600 joules, positive work. And if you look at the work energy theorem, the net work is equal to 1/2 mvf squared minus 1/2 mvi squared. The net work was 600 joules. The initial kinetic energy was 0, so that means the 1/2 mvf squared, or the final kinetic energy, is equal to 600 joules. So that's your answer for number 1. Number 2 is asking, what is the speed of the refrigerator after 8 meters? Well, after 8 meters it had this much energy, and this was the formula for kinetic energy, so really we just want to solve for Vf right here, and that way we could get the speed. So if you solve for Vf in this equation right here, Vf is 3.76 meters per second. So that's the speed of the refrigerator after 8 meters. Number 3, we're going to let go of the rope. So we're going to stop pulling, and the refrigerator is going to slide to rest. Okay, and the question is, how much work will friction do bringing the refrigerator to rest? Well, remember, the kinetic energy of the refrigerator, once we let go of it, is 600 joules, because that's how much positive net work was done. And so in order for the refrigerator to come to rest, the kinetic energy has to go to 0. When the kinetic energy equals 0, there's no velocity. Therefore, you know the refrigerator is not moving. So that means friction needs to do negative work. And it needs to do negative work equal to negative 600 joules. And if it does negative 600 joules of work, it will have removed all that kinetic energy. Final question, number 4, said if we let go and we let it slide to a stop, in other words, if we let friction do negative work on it to bring it to rest, how far will the refrigerator go? So now we need to look at a little bit more here of the work energy theorem. So the net work changes the kinetic energy. And we know the initial kinetic energy of the fridge, when friction starts to become the only force acting on it, is 600 joules. Okay, and we know the net work is going to be done from friction. So really I could write this part as the kinetic friction force times the distance that the refrigerator slides while friction is applied to it, times the cosine of the angle between the friction and the displacement, that'll be 180, equals the final kinetic energy is going to be 0 when the refrigerator is at rest, minus 600 joules. So if I could find the force of kinetic friction, then I can solve for D. Now when we calculated the 1200 joules of work, right, we were pulling with a rope. So if you remember, the original free body diagram for the refrigerator was 833 newtons of force going down, and then it was 82 newtons equal to the Y component of the rope, and 751 newtons for the normal force. But once we let go of the rope and let the refrigerator slide, then the Y component will be gone. So if we're going to remove the Y component, then that's going to be gone, and that's going to mean that our normal force is going to go back to equaling the weight of the refrigerator, which is 833 newtons. And the reason that's important is because that now will affect how much friction there is. So the kinetic friction force equals mu k Fn. And you know mu k is 0.20, and now the normal force is 833, not 751. So that means that the friction force is going to be 166 newtons. So now up in the equation here, the work equation, you're going to do 166 newtons times D, and the cosine of 180 is -1, so this is going to be negative, equals negative 600 joules. You do this division, and you find that the refrigerator slid 3.6 meters until it came to rest. And so that's how you do that.